Okay, this is Math 2413, the solutions for the sample problems for exam 3. Let's take a look at problem number 1. It's a pretty much straightforward double integral. Happens to be in dx, dy order. It's already set up for us. So we'll take first integral, antiderivative with respect to x. So that's going to give you a 1/3 x cubed, the antiderivative x squared. So I brought the 1/3 out here. Here's the x cubed. Then we'll plug in the y and the 0. And that's going to give you y cubed, and then 0 will give you 0. So it kind of wipes out that part of it. So you're just left with y squared times y cubed, which is y to the 5th dy. And then the antiderivative of that will be 1/6 y to the 6th, with the 1/3 still sitting there from before. So we have a 1/3, a 1/6, y to the 6th, 3 on top, 1 on bottom. So it's 1/18 times 3 to the 6th minus 1 to the 6th, which then simplifies to 364 over 9. All right, let's take a look at number 2. Number 2 is in dy dx order. So the sine of 5x will just sit there. So the antiderivative of dy will be y. And then that just brings in the upper limit cos of 5x into play here. The 0 won't affect anything, so we won't worry about that. So now you have the integral 0 to pi over 10 of sine 5x cos 5x. And I chose a U-substitution. You could have chosen sine or cosine to be the U. I chose sine to be the U because that way the derivative would be positive. I don't have to deal with any negative symbols. It still would have been okay, but that's why I didn't choose cosine. Just eliminate any potential mistake. And don't forget the chain rule here. So the derivative of sine of 5x would be 5 cosine of 5x dx. Which I didn't write it here, but that brings out this 1/5. When you divide both sides by 5, there's a 1/5. And I like changing the limits of integration. I guess you don't have to if you're not comfortable doing that, but it makes things so much easier because you don't have to go back to your original variable. So if I put in pi over 10, sine of 5 pi over 10 is the same as sine of pi over 2, which is 1. Sine of 0 is 0. So now my new limits of integration will go from 0 to 1, and now the variable is just u. So I'm integrating u du. I never have to go back to x again. Yeah, when I teach Cal 1, I always highly recommend doing the substitution that way. That's the way I teach it, is by changing the limits. All right, u will be 1/2 u squared with the 1/5 in front, makes it 1/10. From 0 to 1 gives you, put in 1 there, so pretty straightforward. That gives you 1 over 10. That takes care of that problem. Number 3. So now here's one where we have to set up the limits of integration. That's when it always gets a little more challenging. So the function we're integrating is xy over the region of triangle 0, 0, 3, 0, and 0, 6. So I kind of plotted those points out. So here's 0, 0, 0, 6, 3, 0. Drew a bounded region amongst those points. Now I had to come up with what the equation of the line was between those 2 points, 3, 0, and 0, 6. But that's just basic algebra. Calculate the slope. It's a downhill line, so obviously it's a negative slope. -2, and then the y-intercept is 6. So the equation of this line is y equals -2x plus 6. Now this is where you choose to go dy or dx order, up to you. I chose dy dx since I already have y in terms of x. That was the main reason, not that it makes it that much easier. If not, I would have had to take this equation and solve for x in terms of y, which wouldn't have been extremely difficult by any means, but it's already y in terms of x, so we'll go with that. So going from lower to upper, we're going from 0 to the line. So it's going from 0 to -2x plus 6. And then dx going left to right. Remember, the outside limits of integration must always be numerical. So the fact that the equation varies on the inside doesn't matter here. It's straight 0 to 3 right there. So now that was the challenging part. The rest of it's not difficult to work out mechanically. So the antiderivative of y with respect to y will be 1/2 y squared. And I bring in the negative 2x plus 6. We still have the x in front. And the 1/2 I brought to the outside. And now we have to just square out that binomial. Just a little algebra there. So what I did here is in one step, I didn't show that I squared the binomial and I multiplied it by x all at once. So that's how I got this term right here, the 4x cubed minus 24x squared plus 36x. Obviously don't do that yourself if you're not comfortable. If you'd rather square the binomial out first and then multiply it. But since that was just basic algebra, I didn't feel like I had to show every step there. So, all right, you got a straightforward antiderivative here. 4x cubed will be x to the 4th. Negative 24x squared. That'll be x cubed over 3. So 24 divided by 3 is 8. And then 36x squared over 2 makes that 18x squared. And then now you just plug in 3, plug in 0, still with the 1/2 there. 0, of course, will just be 0 in this case. 3, plug in 3, get your calculator out. I'm not going to go through all the numerical steps there, but I'm sure I've verified this before as a correct answer. And just plug it right in the calculator, and you'll end up with 27 over 2. So there we go. Number 4. Okay, now this one's already set up for us, so we're just working out the mechanics of it. So the antiderivative dy will just be y, so you'll bring in the upper minus the lower. So it's 4 sine x minus 4 cos x. And then with dx, we just take the antiderivative with respect to x. So the antiderivative, be careful, don't confuse with the derivative. Antiderivative of 4 sine x will be negative 4 cos x, and the antiderivative of negative 4 cos x will be negative 4 sine x, and then you just plug in pi over 2 and pi over 4. And for pi over 2, we're going to get cosine of 0, sine of 1 right here. And then for the lower limit, pi over 4, we get both of these square root of 2's over 2's. So you add those together and you get the square root of 2. And you have a 1 right here, so it's 1 minus the square root of 2. And with a negative 4 in front, so this is technically correct right here. But, well, that's the only answer choice with a radical, but pretend like maybe there were other choices that had the radical in it. So I just distributed the negative and then reversed the order of the terms and came up, matched that answer exactly. So, all right, excellent. Let's take a look at number 5. Just wants us to reverse the order of integration. No calculation involved here. So we need a picture of the sketch of the region of integration. So we've got for x equals y squared. That's just a sideways parabola. And this will just be in the first quadrant because there's nothing, especially with the y here going from 0 to 6, that tells you you're definitely in the first quadrant. So we don't need to drop the parabola around to the negative side because technically, mathematically, this equation x equals y squared, solve for y, really equals plus and minus the square root of x. We only need the positive side. And then so 36 is the maximum x value. Y goes from 0 to 6. Now, sometimes even when you get the graph sketched, knowing the which part to shade, you have to think about that carefully because it depends on how the integral was set up. It's possible that this part over here on the left of the curve might have been the shaded part. So let's think about this. How did I know that part in green is the correct one? Okay. Well, dx means we're going from left to right. So left to right means y squared on the left, 36 on the right. Now the 0 to 6 doesn't tell you anything because even if we'd have shaded this other part, it still would have been 0 to 6 for y. But it's the inside part, the x part, that tells you. In fact, I'll just tell you real quick, had this been the shaded part here where I'm moving the cursor, if that was the shaded part, your limits of integration would have gone from 0 on the bottom to y squared on top. Then it would have been that region. And then now we're going dy dx, so it goes lower to upper. So it goes from 0 to the square root of x. And then left to right for x means from 0 to 36. And there we go. Like I said, it did not ask us to work this one out. Although it wouldn't have been that bad. Yeah, the reversing the order of integration is a skill of its own, basically, even without doing the integral. Now this one, I don't like the wording of this question, frankly. Determine the order of integration. It should say reverse, because you're going to have to reverse this integration. Reason why is you can't integrate e to the x squared. Well, it takes some complicated mathematical techniques. Dx, because you would need like an x out in front or something to be able to do U-substitution. You can't do it like that. So the word determine I don't like here. So think of that as being reversed. But anyway, let's look at what we have. So you see x is going to be y over 8. So that means y is the same thing as 8x. So I kind of drew a steep line right there. And then x goes from the y over 8 left to right to 7. So I drew a vertical line at 7. And then upper is 0 to 56. And once again, I knew it was this bottom triangle because of this right here. Y over 8's on bottom, 7's on top. So that's how I knew it was that triangle and not the one above it. Or to the left of it, I should say. That's the reason. So let's reverse this thing, and then hopefully it can be integrated, which obviously that's the idea, because it wouldn't be much of a problem. It certainly wouldn't have answer choices if you couldn't do it either way, but so it means it pretty much has to work the other way. So yeah, change it dy dx. Now let's look at what we have here. Now we're going lower to upper. We're going from 0 to the line y equals 8x. So it's going from 0 to 8x, and then left to right, it's going to go from 0 to 7. And then there's that x that we need to be able to perform the integration. That was key for our U-substitution. So the 8 you can just bring to the outside, whatever you want to do. But you let u equals x squared, which means the du will be 2x dx. Now I didn't actually show the divide by 1/2. But you would divide both sides by 1/2, which is producing that 1/2 right there. And then, as I mentioned earlier, I'm a big fan of the changing the limits of integration. So u of 7 squared would be 49, 0 squared would be 0. So now I have the 8 from here, the 1/2 from the du. I'm now going from 0 to 49, e to the u du. And that's such a wonderful antiderivative because you can't really mess it up. You don't have to add 1 or anything like that. The antiderivative of e to the u du is just e to the u. Now I don't have to go back to x because I changed my limits of integration. So I just put in 49, I put in 0. Now a lot of times you got to be careful running, which we've had these other problems a lot of times. When the lower limit's 0, most of the time it produces 0 at the bottom, but you have two common functions where that's not true is e and cosine. Because if you plug in 0 for either one of those, it's going to be 1. So that's what's happening here. So this 0 on the bottom doesn't automatically 0 out here like it does for other problems. So the 4, I just left it out there. E to the 49 minus e to the 0, which is 1. So therefore in there it matches that answer. All right. Sometimes you can fall into that habit of automatically thinking 0 is always 0 when you plug it in. It is for like polynomial terms, like x squared, x cubed, x fourth. Yeah, then it's 0. But not for e or cosine. Okie doke, let's see what we got here. We're going to need another reversal because you're not going to be able to integrate this quite with what we have there. Sort of looks like it could be done as an arc-tangent type of problem, but we're kind of missing. We wouldn't, if we let u equal y squared, we need a y in the numerator for this to work as arc-tangent from back in Cal 2. So that's what's missing here. So sketch the graph. So y equals cube root of x, just kind of comes along sort of like the square root of x, like so. I know that y is going from, x is going from 0 to 27. And it's going from the curve to 3. So this time, the shading, once again, obviously is important. It's the upper part, because the limits of integration say cube root of x on bottom, 3 on top. So it goes from here to here. And so now, if you have y equals cube root of x, that's easy enough to solve for x. If you cube both sides, that gives you x equals y cubed. All right, right here. And let's see what would happen reversing it now to dx dy. Dx dy means we go left to right. So you're going to go from 0 to the curve, y cubed. So it's going to go from 0 to y cubed. And then the dy on the outside is going to go from bottom to top, 0 to 3. And there we go. This is going to work out well. It's going to work out nicely for us because we're going to end up with a U-substitution integral. Because the first one's dx, so this just sits here for temporarily. It's just a constant. So dx makes it x, and then I didn't write the x here, but all you're doing is bringing in the y cubed, because y cubed minus 0 makes it y cubed. Now, so for the last outside integral, it's just substitution. So you let u equals y to the 4th plus 1, du equals 4y cubed dy, so 1/4 comes outside. And then I change the limits of integration, put in 3 to the 4th plus 1 is 82, 0 to the 4th plus 1 is 1. And now we have du over u from 1 to 82 with the 1/4 out there. Du over u, that antiderivative is natural log of u. So we have 1/4 natural log of u of 82 minus 1. Now you might have wondered what happened. Did I forget something here? No, I did not, because natural log of 1 is 0. That's why it's not there in the answer. So, on a handwritten type exam or something, obviously somebody could write minus 1/4 ln of 1, and if they didn't realize that was 0, that's okay. I would never penalize someone for that. But that's why. So the 1 was plugged in there. You just didn't see it. ln of 1 equals 0. Okay. Terrific. Okay, we're going to take one of these ones like I did in the notes, and we're going to kind of combine it together. If by reversing the order it happens to combine together into one integral. Not every, and there was one, my notes that I had there too, and early on that, not every time where, 2 doesn't always merge into 1. Sometimes 2 is still going to be 2, but you can tell by these answer choices that it's not going to be 2 of them for this one. It's going to be 1. So you see that I have dx here. I'm going from 0 to y, so I graph the line y equals x, or x equals y, same thing. That's coming this way. And then over here we have an 8 minus y, so I just solved x equals 8 minus y, which is y equals 8 minus x. So that's this line coming down this way. And they intersect at 4. That's super easy to solve, because you can just put in x equals y from the bottom equation to the top, and you would get 2y equals 8. This one, and plug this into here, you get 2y equals 8. 8 equals, so y would be 4, and actually x would be 4. So it's hitting at the point 4, 4. So let's see. And then it's going to be this inside, well, the rest of it's unbounded, so it has to be right here. this inside triangle. Now the reason why this was two separate integrals before, probably should have drawn. Let's see if I can just kind of put this in here freehand. I'm using a computer that's not using a stylus here, so I would have to just try to do this with my mouse pad. Just kind of go like this a little bit, just kind of draw some dashed lines, or like I did in my notes. In case you were wondering, why was it two integrals to begin with? Okay, good question. I can answer that. It's because dx dy means left to right. So left to right, you have two different right functions. So I drew that dashed line to show you where they separate. So below the dashed line, you have a left to right here, and then above it, you have a left to right up there. So that's why it was two of them. And then you see it's going from y was going from 0 to 4 for the bottom one, and then the other one's going from 4 to 8. So there it all tidies up real neatly. Now the question is, why does this work as one double integral this time instead of two? Well, left to right we had an issue, but lower to upper we do not. If we start with go dy dx, we have the same bottom graph, x equals y, and the same upper graph, x equals 8 minus y. There's no change over there. It's the same lower, it's the same upper. So therefore, it's one double integral. That's why. So dy dx, we'd be going from, so you have to reverse it now, y equals x. So we're going from x on bottom to 8 minus x on top. So it goes from x to 8 minus x, lower to upper, and then left to right would go from 0 to 4. And there we have it. I like that problem. Excellent. So number 9, we're going to use a double integral here to find a volume. Z equals x squared plus y squared. So we're basically doing the double integral of the function z f of x, y. Dy dx, in this case, I don't think makes much difference. Not like the problems we showed earlier where you had to reverse it. The order, it was order specific. Not so much here, but I'm just going to use the argument that I already have y in terms of x. I want to put dy first. That's the only reason. So I drew the line. That's y equals 3x. I didn't label it, but I'm sure you would have figured that out. 2 and then 6. And once again, how do I know it's the lower one? Because it's bounded by the line y equals 3x. X equals 2, this dashed line, and y equals 0. So basically in this description up here, that's what's telling you. Unlike the other problems, if it had the limits of integration, we were looking at it from that point of view. Here we're looking at it from the description that's telling you that it's bounded just like this, that triangle. All right. I just kind of drew the 6 up there. We really didn't need it, but I just sort of showed that's where, it was hitting for y. But we don't need that. So we're going to integrate x squared plus y squared dy dx. We're going to go lower to upper, 0 to 3x. And then left to right, we're going to go 0 to 2. And the first one's antiderivative with respect to y. So I do that. So it's going to be x squared y. And then y squared will be y cubed over 3. Plug in 0, plug in 3x, so you get x squared times 3x will be 3x cubed. And then you have 3x all cubed, which will be 27x cubed. 27x cubed divided by 3 will be 9x cubed. Oh, okay, so you can see, now they're like terms. You can integrate them separately if you don't recognize that they're like terms. But that's what I did. I added them together and treated it as 12x cubed. And then the antiderivative of 12x cubed would be 12x to the 4 divided by 4, which is 3x to the 4th. We put in 0 and 2. So I just put the little maple graph here showing you what the thing looked like. And then there's the triangle region there on the bottom. I just kind of drew these lines showing you that's what you're actually finding, the volume that it cuts up out that base when it cuts up into the surface. How much volume is that? Cut out by that little section right there. And it's 48 cubic units. Don't worry about units, but it would be cubic units because it's volume. All right, let's take a look at problem number 10. Setting up a region to find a volume with the given base of the function you're integrating right here, z equals 7x plus 2y. And as I mentioned down here, after working this out, I thought about it, and a little too much work, I think, to have you do this on an exam. It's not hard math, it's just very, very tedious and a lot of details to keep track of, which makes it tough for multiple choice. So the important thing on this is just let's focus on the setup. Now it's two double integrals, and actually it's two double integrals no matter what order you choose. And I would probably only have one of the two, if I had this on a test, so you would know kind of what you were looking for in the answers. They'd either all be dy dx or they'd all be dx dy. So this one I did here dx dy, and I'll show you dy dx here down a little lower here. But so we'll kind of skip all the mechanics. You can look at that if you want to and try it if you like to practice or whatever. But let's just get the setup on this thing. But yeah, this one's definitely two double integrals either way. And unlike some of the other problems that you had to maybe add two double integrals if you picked one order, but if you picked the other order, it was only one double integral. Not true here. Because this one, if you go like where that line's drawn, you go left to right, red to blue, red to black, two different rights. If you go lower to upper, it's two different uppers. It would go red to blue, blue to red, and then blue to black. It would separate. So it's no easier the other way, I promise you. Although the limits of integration don't have fractions in them, that might be the only thing. We'll scroll down there and you'll look and see what I did. Of course, you can already look at the file and see what I did. So let's take a look at this. Now to go dx dy, so I graphed all three of these, and it's that bounded triangle between them. I have to get x in terms of y. So below the line, we're going from left to right, means red to blue. So yes, it's y equals 2x to y equals x, but they have to be x in terms of y. So y equals 2x is the same thing as x equals y over 2, and then x equals y. So it goes from y over 2 to y, and then the upper dy is going to go from 0 to 3. 3 is the point of intersection for x between these two values right here. Easy to solve. If you put x in there in terms of y, you get 2x equals 6, x equals 3. But y, that means x equals 3, but then y would also be 3. Because at that point right here, y equals x. So it goes from 0 to 3. Right there. Y over 2 to y, and there's the function you're integrating from right there. 7x plus 2y. Come over here. Now we go from 3 to 4. The reason why we know that's 4, other than just kind of looking at it on the graph and seeing that it's 4, but just mathematically determine precisely why it's 4, is if you set the red and the black equal to each other and solve for x. We ultimately need y. I guess you could solve for y, but I'll just solve it for x and I'll get y. So you set 2x equals 6 minus x, which will give me x equals 2, and then I can put 2 in for x into either one of those y equals, and I'll get 4 for that value right there. So it goes from 3 to 4, and then left to right this time. It's the same y over 2 on the left, but on the right side now is then, so if you take y equals 6 minus x, and you solve it for x in terms of y, you will get 6 minus y. So there's the setup. Here's the mechanics of working all this out. So just a little tedious, so don't worry too much about that. Just focus on the setup, and you get 49. Now I come down here and take the same picture, and I'm going to show you the other way. dy dx. And you can see my answer, I'll just let Maple do it, software, and you can see my answer is 49, so it would be quite the fluke if this was not correct. In other words, since that 49 matches, that probably means I have both of them set up properly. But let's look at it. So now, instead of a horizontal line, you split them by a vertical line because of two different uppers. So it goes lower to upper, red to blue, would be x to 2x. Let me focus on that, then I'll come back and look at the numbers. Then the upper right, the right of that red line will go from blue to black, will go from x to 6 minus x. Now the x value, just like I solved it before, you set the 2x and the 6 minus x, these two equations, the red and the black, equal each other. You'll get x equals 2. So you're going from 0 to 2 for the first one, where it separates the red line. And then you can solve the blue and the black equal to each other, and you'll get 2x equals 6, and you'll get x equals 3. So then the second integral will go from 2 to 3, and then therefore that will yield, that result then also yields 49. So either order would have correctly solved it, but it did take the sum of two double integrals, no matter which order you took. So evaluate by using polar coordinates. This one's a pretty easy one. Now, y equals the square root of 9 minus x squared. It's the same thing as x squared plus y squared equals 9, which is, of course, a circle. So I drew that circle. And since y is going from 0 to that square root, that means I know it's just the upper half. No, it's not below the upper half. That means it's either going to be quadrant 1 only or both quadrant 1 and 2. See, the next one will tell you whether it's just the first quadrant or the first and the second. But the dy tells you it's definitely not below the x-axis. Now, x is going from negative 3 to 3, like here at negative 3 to 3. So there you go. That's the negative 3 to 3 means it is covering both quadrant 1 and 2. That's important because your theta, your limit of integration for theta, then will be 0 to pi. So the radius r will be 0 to 3. And always remember, when you convert from rectangular to polar, whether it's dy dx or dx dy, you always have that added r in there automatically, r dr d theta. Now there might be some other functions of r and theta in here, but dy dx, dx dy automatically convert to this extra r right here. So this is pretty simple. You now integrate, so r will be 1/2 r squared. There's the 1/2. Put in 3, put in 0, makes that a 9, so it makes it 9/2. Then we go 0 to pi, and then d theta. And then that just makes theta, so it's 9 pi over 2. And there we have it. So it'll be 9 pi over 2. Which actually, this problem, it's better when you're integrating an actual function, because all you're really doing is finding the area of a half circle, which you could have done using geometry. But this just gives us good foundation on using the calculus, because we obviously need to do so in other problems. But yeah, the area of that total circle would have been 9 pi, so half of it is 9 pi over 2. But as you well know from the notes and other studies, that we're not always just finding the area of a circle, of course. Prime example right here. So we have a circle with radius 8 based on this. Both lower limits of integration are 0, so that guarantees we're confined to the first quadrant only. So that takes care of that. So that just means we know we're going to be going from 0 to pi over 2. And then the radius will go from 0 to 8. Square root of 64. And then now, x squared plus y squared is r squared, so it gives you e to the negative r squared, and then dy dx converts to r dr d theta. So obviously that was very convenient for us. That, of course, that's the correct way to do it, but it converted over, and we needed that to be able to for U substitution. So I'm letting U equal negative R squared, which means du equals negative 2R dr, which brings out a negative 1/2 out here. And then U of 8, put in 8. Be careful here because some people make this mistake. The negative, you don't, without parentheses, you don't square the negative. So it's the negative of 8 squared. So it's negative 64. Of course, 0 will be 0. So 0 to pi over 2. Then we have 0 to negative 64. E to the U du. And then d theta for the last one. E to the U du will be simple enough. It's just e to the u. Put in the negative 64, put in the 0. Now, I used a little trick back from Cal 1 here. I didn't show that, but I'll explain it right now. Is when you reverse the limits of integration, that creates a negative. And I just wanted to get rid of that negative right there. So by flipping around, I didn't write it that way, but I solved it that way. Flipping around the 0 and the negative 64 created a negative, which took out that negative, so it makes it positive 1/2. E to the 0 is 1. And of course, that's just the e of the negative 64 right there. And then 0 to pi over 2 d theta. There are no thetas in this problem. So it just produces a theta, which produces a pi over 2. So pi over 2 times 1/2 makes that pi over 4. And then 1 minus e to the negative 64. There we go. So let's see what we have here. All right, so yeah, with both these lower limits being negative, we've got a full circle here. Because that means x can be negative, y can be negative. Just goes around the entire circle. No problem. So circle with radius 4, square root of 16. So we're going 0 to 4. That would have been 0 to 4 no matter how much of the circle we covered, but 0 to 2 pi because we're covering the entire circle. Now, x squared plus y squared, of course, is just r squared. Then you have r squared to the 5/2. And then, of course, your automatic r right there that goes in there every time. So r squared to the 5/2, multiply the exponents. That's r to the 5th. R to the 5th times r makes r to the 6th. So the answer looks a little weird because of the size of the number, but it's a very easy problem. And we integrate r to the 6th with respect to r. That will be 1/7 r to the 7th. Put in 4, put in 0, so that's where the large numbers coming in there is because 4 to the 7th power equals 16384 over 7, 0 to 2 pi. Just brings us the 2 pi in there, so it just doubles the numerator. So it makes it 32,768 over 7 pi. Find, number 14, find the area of one leaf of the polar rose curve. All right. I did these kind of problems in Cal 2. It's kind of the same idea here. Should have put a picture of the graph in here, but that's okay. You really don't need it because you just need to know when we'll, when you start at, if theta equals 0, you're starting at the graph will start at 0. In fact, let me pause this and I'll put a picture in here. Okay, I'm resuming the video here so you can see how this is graphed. But that's not going to be an issue. You're not going to have to graph it. I just want you to be able to look at it here and see what's going on. I'm going to put this in mode, polar mode. And I'm going to quit out of this. And now the y equals will be r equals. And I believe it's, what, 3 sine of 2 theta? Yeah. And theta will be x now. And I'll change the window. Let's see. It's going to go, yeah, 6.28. That's 2 pi. I don't really need, because with that 3, that means the farthest, I'll use 5 here, but the farthest is ever going to go out is to 3, but I'll give it a little room here. So I'll go negative, yeah. It would have looked a little small if I could have zoomed in, obviously, but so let's just do that so we can get a better feel of what it looks like. There we go. Actually, let's see. And I'll snip this out and paste this in though. So we're going to do that first one. And so when you put in 0, you're going to get 0. We just have to figure out what value of theta returns it back to 0. That's the key on setting up the integral. All right. Let me put the pick. I'll just put it down here. So what I did up here is to graph that first petal. 0 will be 0. Now, the key is this 2 theta here. In other words, the next time on the unit circle that sign will be 0 is whenever you hit pi. Sine of pi will be 0. But notice that this is 2 theta right here. So I don't need to put pi. Yeah, sine of 2 pi is also 0, but that's not what I want. I want the next time it gets back to 0. So actually, if theta is pi over 2, you put pi over 2 in there. Sine of 2 times pi over 2 will be sine of pi, which is 0. The easiest way to remember this is just take pi and divide it by whatever the coefficient of theta is. That's how you do it. That's the logic by. So if that would have been sine of 5 pi, theta would have been pi over 5. So we're going from theta to pi over 2, 0 to 3 sine 2 theta. And you have RD theta. Now I worked this out, but really it's only, so you put the first one in there once you get down to the last integral. So you have 1/2 r squared, you put that, you have 3 squared will be 9, so 9 comes out, 9/2, and you have sine squared 2 theta. There's nothing really stopping you from, if you want to do the numerical integration in the calculator, that's fine without having to work it out. Not much I can do about that. So, but anyway, this one I had to use an identity. For sine of 2 theta, it's 1 minus cosine of 2 theta, so it doubles the angle divided by 2. Cosine squared is 1 plus cosine of 2 theta divided by 2. They both use cosine, just one is minus and one is plus. But yeah, you can numerically integrate this if you want to. So that brings out a 1/2, makes that 9/4. 1 minus cos of 4 theta. Antiderivative of 1 is theta. Antiderivative, because of U-substitution, whatever, cos 4 theta will be 1/4 sine of 4 theta, the du. Put in pi over 2, put in 0. You get a bunch of zeros here. The only term that's not a 0 is the very first one. You put pi over 2 in there for theta. And you end up with 9 over 4 times pi over 2. Everything else is 0. We get 9 pi over 8. There's the graph. Now you can also use numerical integration for this if you like in the calculator once you kind of figure out the setup here. Now this one's not too tricky because this one's going to be 0 to 2 pi. There's not going to be, it's not as tricky as the leaf thing or whatever. It's just going to be straight up 0 to 2 pi. So it's going to go from 0 to 8 plus cos theta, 0 to 2 pi, r d theta. So we have this is not real critical, but I'm just showing that, r of 0 gives you 9, then r of 2 pi takes you back to that same 9. So anyway. And so our antiderivative would be 1/2 r squared. Put in 8 plus cos theta. So 8 plus cos theta squared, which you have to FOIL that out. It's not just 64 plus cos squared. You got to FOIL it out, and you have a middle term here. And then this time, okay, I split this up into 2 pieces. Yeah, because one of them's going to have a fraction. It doesn't have to be done that way, but it's whatever. Like I said, at this point, you can put it in the calculator and do it if you want to. But anyway, I took the first 2 terms, and then this, because I had to use this identity. So cosine squared will be 1 plus cosine of 2 theta over 2. In my notes, I think I've done, well, maybe not in the notes, maybe I'm thinking of Cal 2, but I kept them all together and got kind of a common denominator for all of them and pulled it out. Could have done it that way. This one, I guess I just chose to split it up. So not hard to integrate from here. 64 will be 64 theta. 16 cos will be 16 sine. And then I pulled the 2 out here with that 2 to make it 1/4. So I'm just integrating the top part. 1 will be theta. Antiderivative cos of 2 theta will be 1/2 sine of 2 theta. All right, so you plug in 0, you're going to get 0 because there's no cosines here. Be careful, obviously if there's cosines, that's different. But since everything is sine, when you put the 0 in there, it's going to be 0. Same thing for the 2 pi. So the only thing that's going to produce any action here is just this first number. 2 pi, you plug that in there for theta, gives you 128 pi. And then over this integral, you plug in 2 pi for theta. You get 1/4 times 2 pi is pi over 2. Then basically it's 64.5 pi, which is the same thing as 128 over 2 plus 1 over 2 is 129 over 2 pi. There we go. All right, number 16. Region bounded by the paraboloid in the xy plane. Finding the volume. This is a picture of it. You're sort of looking at it downward here, from above. We don't really need let's see if I did graph it, but I didn't. Did I graph it? No. But you don't need to. It's a pretty simple function to deal with. You're obviously, when I say graph it, I meant would I be providing the graph? You don't have to graph it, obviously, but because all we care about is setting up the limits of integration on the base. Because we're integrating, see, it's the double integral of the z, which gives you the height and then the base together, and that makes the area of the base. That makes essentially the volume. Now, watch for restrictions. Sometimes it might say, but don't put any that aren't there. It may say, oh, okay, but x is greater than or equal to 0, or y is greater than or equal to 0. So with no restrictions like that for this problem, you can assume it's 0 to 2 pi. You can absolutely make that assumption. And then it's a circular base. In other words, pretend like if you're on the xy plane, that means z would be 0. So essentially, if you solve this equation equal to 0, you get this. X squared plus y squared equals 16. Now we're definitely going to do this in polar coordinates because it's so much easier. And x squared plus y squared becomes r squared. So you have 16 minus r squared right here. And then the r that goes in there every time. R d theta. Radius will go from 0 to 4. Theta goes from 0 to 2 pi. So not too difficult. So we have 0, so it's going to be 16r minus r cubed. After you multiply, there's not integration. I'm just distributing the r first. You could use substitution, but this is much easier. distribute the r, then take the antiderivative. We got 8r squared for 16r, minus r to the 4th divided by 4. And 0 to 4. And plug that in there. 8 times 16 is 128. 256 over 4 is 64. So it's 64 d theta, which makes it 64 theta. Multiply that by 2 pi. We get 128 pi. There it is. Number 17. Region bounded by paraboloid, the cylinder, and the xy plane. So we're looking, so the xy plane, the base, and the region's going to be inside, so the cylinder is going to hit the paraboloid. So it's outside the paraboloid, but inside the cylinder. That's the only way it would stay trapped. Otherwise, it would just be unbounded this way. So, let's see what we have. The function we're integrating will be z equals r squared, because x squared plus y squared equals r squared. It looks really complicated, but it's not. It's not too bad. It's r squared, then of course your r d theta. So we're going to go from on the plane now. The height's the r squared, so we're only looking at the base. It's a circular base. In other words, kind of like the last one. You just essentially, just focus on that circular base right there. So the r is going to go from 0 to 6 with no restrictions. In other words, about x and y being positive or whatever. So it goes 0 to 6, and that makes this then go from 0 to 2 pi. No restrictions for x or y. So once you get this set up, it's not too bad. R cubed will be 1/4 r to the 4th. Put in 6 and 0. 6 to the 4th is 1296. 1296 divided by 4 is 324. 0 to 2 pi. D theta makes that theta. So then it's just 324 theta. Put in 2 pi, put in 0, so you multiply it. And you get this answer right here, 648 pi.